Okay. Okay, so probably you can see the slides full screen now.
Yes, so we can begin if you are ready.
Yeah, sure.
Okay, so welcome everybody to this year's Majorana-Raychaudhuri seminar series. We are happy to have Sadra Jazayeri from Imperial College, UK, and he's going to talk about uplifting massive graphs from Minkowski to de-Sitter. I'll send you a reminder when 5 minutes are left.
Sure. Yeah, thanks a lot. I thank the organizers for the invitation. It's a wonderful pleasure to give a seminar in this Majorana-Raychaudhuri series. So please also feel free to interrupt me, or Anish, please forward to me any questions if there are in the chat or
Sure.
on the YouTube channel. Yeah, don't wait until the end. So yeah, today I'm going to talk about a recent work that we posted to archive in collaboration with Sebastian Cespedes, also at Imperial College. So it's about cosmological correlators and bootstrap. So I will therefore start with an impressionistic overview of the bootstrap program for cosmology. Then I will move on to the flat space limit of cosmological correlators, first motivating why the question is interesting in the first place. What do we learn by taking the flat space limit? Then I will review the old results and introduce an upgraded flat space limit today, the massive flat space. And finally, I apply this new flat space to actually make new predictions for paramoidal non-Gaussianity related to the signatures of heavy fields during inflation. So starting from Bootstrap, okay, just what is Bootstrap? Maybe you wonder if you're not familiar with the CFT Bootstrap or Amplitude Bootstrap. So Jeffrey Chu, actually the founder of the Bootstrap program for particle physics, was once asked this very question, and his answer is very interesting. So he says that the idea tends to evolve in time, and the key notion is consistency. So the answer is interesting if you look at the date of the interview in 1984, which is already a couple of decades past the peak of the S-matrix bootstrap program, which started with the radical idea of nuclear democracy. So at that time, physics was in a sort of weird situation. So we were discovering new particles, new hadrons, and we didn't have a very good picture of we didn't actually have any picture of how to describe this pool of particles using the available quantum field theory methods. So some physicists actually like him took a temporary divorce from quantum field theory and Lagrangian and just started thinking of these particles just as elementary as any other particle and focused on the observable, the S matrix that involved the strong interactions between these particles. So the hope was that starting from the principles of special relativity and quantum mechanics, we can find a complete framework that just by consistency spits out these S metrics, and the consistency conditions are just so strong that they uniquely give you the final answer. So of course, by the advent of QCD and quarks and so on, so this point of view was largely abandoned by physicists. Still, it left behind very interesting legacies. For instance, the string theory itself was inspired by the discovery of the Veneziano amplitude, one amplitude that came out of this program, which corresponded to the exchange of infinite number of spinning mesons. And there were many interesting insights into the analytical structure of the S matrices, dispersion relations, so on, many of which are documented in this sort of Bible book of the S matrix, the analytic S matrix. But then, starting from mid-80s, people started using the same ideology, but in a different way. So the different way was that just again looking at the Lagrangians, people started using the principles of unitarity, analyticity, and locality in the UV to constrain the space of low energy effective field theories, especially the chiral Lagrangian. And that point of view is still going on so in the modern S matrix program, and people are still using this point of view to understand the low energy phase of QCD and other sort of gravitational and gauge effective field theories. And parallel to these developments, of course, people were also working in the trenches to apply the ideology of Bootstrap, but this time to just pick a couple of theories. And they came up with these very powerful on-shell methods for computing even perturbative processes. And this point of view, I've discovered many interesting relationship between amplitudes, many simple structures within the amplitudes that are like double copy, that are otherwise completely hidden from the ordinary Lagrangian perspective. And this perturbative S-matching bootstrap is really the successes here that drives the cosmological bootstrap that I will be discussing today. So in the context of cosmology, uh, it is especially appealing, the bootstrap ideology, to be applied to the initial condition of our universe. So I'm talking about inflation. So in the beginning of the universe, there were this exponential expanding phase that we call inflation, a very quantum phase, out of which the universe was born. And then when the inflation ends, we have this reheating surface from which the Big Bang, the hot Big Bang starts. And then the universe is really classic. So before this phase, one reason that it's interesting to apply this bootstrap ideology, just the general principles, is that when we usually write down models, so on and so forth, these are the stories that we came up about the history of the universe. So what fields were there? So how the universe, how the expansion worked, what were the quantum fluctuations, what were the interactions. So all of these stories are really in the just infer them from the information that are available on the boundary. So it would be very efficient instead to come up with a framework that only talks about this boundary information and just try to constrain them using general principles. There are other reasons that you want to apply the bootstrap ideology, for instance, just the inflationary model buildings. It's very inefficient because usually when you go through the nuts and bolts of individual models, they have far more features than we can realistically ever observe. So it is more efficient to just look at a selected number of observables, for example, the bispectrum or the trispectrum, and then try to constrain that observable using principles instead of just looking at many degenerate models. So there has been many works in recent years. This point of view has gained momentum. This is a very incomplete list. There's also been some developments on the non-perturbative bootstrap side in exact rigid de Sitter, although I will have nothing to say about this second part. But on the perturbative side, our collective efforts has been to start from general principles and come up with a list of consistency conditions that the final inflationary correlators should satisfy. And unlike the more radical bootstrap idea that we didn't want to look at Lagrangian here, we don't feel shameful to cheat from the Lagrangian sometimes and just extract information and refine our list of consistency conditions. And sometimes it happens that these consistency conditions are so powerful that they just uniquely fix the final correlator, even if it's just a perturbative diagramming that we are computing. So cosmological bootstrap has uncovered interesting features of correlators that are usually difficult to observe using the more standard frameworks like in perturbation theory in time-dependent backgrounds. And today I will have only one aspect to focus on, which is the relationship between correlators and scattering amplitudes. This is also something that is not very obvious from the Lagrangian perspective in the standard form, but it makes sense when you analytically continue the correlators, as I'm going to discuss. But before going through the details, I will inevitably have to lay out some formulas, some definitions that I have collected in a couple of slides. So first of all, about the metric. So during inflation, I approximate the background expansion with an exact de Sitter space. This is a very good approximation of two slow roll corrections. So the de Sitter here is charted in the Poincare patch with the conformal coordinates eta and x. So eta runs from minus infinity. This is in the flat space limit all the way to eta equals 0, which is the end of inflation or the reheating surface. And then the quantum field theory that I will be working on during inflation, I will be thinking about during inflation, is a very simple one. It only has 2 degrees of freedom, just for simplicity. A light degree of freedom phi, and also a matter field sigma. So phi, I'm at the back of my mind, I'm thinking of it as the observable sector. So this is the scalar fluctuations during inflation that at the end I'm interested in its correlation functions at the end of inflation. And sigma is some let's say spectator massive field that is coupled to the inflaton field, but I do not directly observe it. I just see its effect only through the exchange processes in the correlators. And usually this matter field, this sigma, I assume that it belongs to the principal series of the Ceter, which means that its mass is bigger than 3½ Hubble in 4 dimensions. So in cosmology, usually just to make the special translation manifest from the very beginning, we switch to momentum space K. So this is the vector K. So we don't have energy, unfortunately, in cosmology because we are in an expanding background. So we have a time-dependent background and no conservation of energy. But we have conservation of a special momentum K. So I will refer to the size of the norm of K with the unbold letter K. So in absence of interactions, quantum fields just propagate freely in the Ceteris space. The propagation is characterized by either positive or negative frequency mode functions. For instance, the massless field has this form, which resembles just the plane waves in flat space. It's slightly different, but it is simple. Therefore, computing usually the correlation functions that only involve the interactions of massless fields are simple. However, as soon as you go beyond massless or conformally coupled field, things become challenging as the mode functions already are Hankel functions. So these are very nonlinear functions. And that's one of the reasons that explicit brute force computations in the Ceter is hard. And eventually, I'm interested to look at correlation functions of the massless field. For instance, the equal time correlation functions of the massless field at the end of inflation. And just like flat space in perturbation theory, you can organize the computation into a set of diagrams. So for instance, this is a one loop diagram that contributes to the 4-point function of the massless field, which is characterized by 4 momentum. Of course, this block will be proportional to a delta function that conserves the special momentum. So the diagrammatic rules in cosmology in an expanding background are also different compared to flat space because of the path integral that we are essentially computing when computing this diagram. The corresponding path integral is of an in type. And due to that, it has a different structure. In particular, the vertices are of 2 types, plus or minus. And when you connect the vertex to the boundary, you get a box-to-boundary propagator, K plus or K minus, which are built out of the positive and negative frequencies. And each vertex that you add to your diagram, you're adding one more layer of time integration. And when these vertices are connected together, they come in, they spit out 4 different types of bulk-to-bulk propagators, only one of which appears in the flat space computation G++, which is the time-ordered Feynman propagator. So it is more complicated, and putting everything together, usually the structure of the correlation functions attributed to a specific diagram is of this type. So you have a sum over all the possible variations of the vertices, plus and minus. And then you have appropriate insertion of the propagators and also probably some remaining loop momentum, a special loop momentum that you have to compute. So what is important here to note is that these integrals are nested time integrals, and there is really no further step to simplify these integrals because, as I said, there is no time translation symmetry. So I cannot just like in flat space switch to energy space and
Hi,
simplify.
there is a question from the audience
Yeah.
asking that can one directly compute amplitudes in the de-Sitter instead of using correlators, using free asymptotic states as Bunch-Davies vacuum, or one has to resort to some static patch? More specifically, what is the reason to compute only correlators and not amplitude in cosmological vacuum?
Yeah, so yeah, the first reason is just observational because even if you can define asymptotic states in the Ceter, which is a big if because it's a difficult thing. So if you look at the Poincare patch in the infinite past, you have free fields. Really, you can just assume that I mean, usually we assume that you are in the vacuum and then the universe expands. But just defining asymptotic states is not possible because so even in the infinite past, the particles are just as close as become as close as possible together, just because you just go back in time. So just switching off the interactions in the infinite past is tricky. Therefore, just defining S metrics is tricky. But just observationally, these correlation functions are really what you observe in the sky. So it's not so you don't have access to S metrics like control over the in and then observing the out particle. Well, the only thing that you measure are just the correlation functions of galaxies or the CMB temperature, and all of these at the end are related to the correlation functions of quantum fields at the end of inflation. So I hope this answers, but yeah, we can discuss more if there were more questions. Okay, so imagine that despite this complicated graph, someone has cranked through a very difficult computation and gives you the final answer for a specific correlation functions. And then you want to run some consistency check. And one consistency check, you could say that, okay, so in some limit, I expect that I should go back to flat space. So you might ask, well, what is this limit? So maybe the limit is that you have these correlation functions as a function of momentum. So you send momentum to infinity, and momentum to infinity corresponds to a smaller scales probably, and then a smaller scales correspond to flatter space. So this expectation is wrong because you should not really think of the momentum k as an energy scale. It is more like an angle that characterizes the configuration of an endpoint function. This is due to a scale invariance because when the universe expands to infinity, on the asymptotic boundary, things are a scale invariant. So by just cranking up the momentum, in fact, by just rescaling all momentum with a number lambda, the correlation function just rescales with the power law. So you don't recover any interesting information by going to infinite momentum. So what you should do is to just get more creative and just resort to analytical continuation. In particular, if you take this particular limit, which we sometimes with a bit of a misuse of word, we call this quantity the total energy of a graph, KT, which is the sum over the norms of the vectors. If you do the analytical continuation, you can actually send this to zero, which is not possible with real momentum, but with complex momentum, it is accessible. So if you take this limit, you will observe that the time integral corresponding to the graph actually starts picking its dominant contributions from very early times when all the vertices are evaluated at minus infinity. So in the infinite past or in the UV. So in the UV, all the energy scales corresponding to the external fields. So these are time-dependent energy scales because of the expansion of the universe. All of these energy scales go to infinity because they scale with 1 over the scale factor. And effectively, everything, all interactions are happening deep inside the horizon because all these energy scales are above the Hubble scale. So you expect that to some extent you should recover some sort of flat space object. And in fact, if you do the analysis carefully, you will see that the correlator in this KT going to zero limit picks up a singularity that comes with a specific power that is the model dependent, but the residue of the singularity is invariably given by an amplitude. And the amplitude corresponds to the same amplitude that comes out of just amputating this graph and putting it in the flat space. So this amplitude is characterized by, for the 4-point function, for example, by 4 external momentum, some 4 momenta. So these are null 4 momentum because they are formed by the spatial momentum k and also its norm. Moreover, the internal lines in these graphs will be massless propagators. Even though I started with a heavy graph, maybe I should also mention that for reasons that become clear, I will be only looking at diagrams that involve the massive internal lines. I will tell you why I'm just restricting myself to that case. So even though these internal lines were massive, when you take this particular limit, all the internal propagators also become massless. So this is clear from the early time picture because you send eta to minus infinity. So all the energy scales just become very large compared to the mass. And there the mass is unimportant. Therefore, the propagators that you get are massless propagators. So the amplitude here is a massless amplitude, both on the internal and external legs. So there are um, reasons to try to revive information about the mass in this flat space limit. It's not very good that we just lose all the information when we take this flat space limit, because I mean the structure of the massive correlators is much more intricate compared to massless correlators. Therefore, you might ask that where are the information about these masses in some flat space limit? And one reason that you want to revive this information is that we already know a lot about the structure of massive Feynman graphs in flat space in the context of Feynman integrals. So there are people that have spent all of their career just working through the structure of these Feynman integrals, and there are very rich structures there, and it would be very helpful to learn something from these computations for de Sitter massive exchanges. On the observational side, of course, looking at correlators with the massive exchange is interesting because these correlators carry observational signatures of massive fields, and these massive fields, the mass is of order of the Hubble, which could be 10 to the 14 GeV. So these scales are closer to Planck scale than the Vika scale. So this will be our only hope to observe, to detect these particles through their signatures in non-Gaussianity. So it is interesting to look at correlators with massive exchanges, and in particular their flat space limit. So the flat space limit, the massive flat space limit that I want to introduce today, it requires me to still lay out some more definitions. So first of all, I will have to look at the broader set of objects compared to the unshelled correlators that I just gave you their definitions in terms of the in rules. So instead, I have to look at off-shell extensions of diagrams, by which I mean that so far the external lines in a diagram, they were associated with the bulk to boundary propagator, which was evaluated at the norm of the momentum k. So the momentum k was related to this norm, and then the bulk to boundary propagator it was inserted inside the in diagram. However, I want to now replace this propagator with a propagator that comes with an independent variable omega, which I call the external energy. So these are things that I introduce by hand. So I just extend the external kinematics, but it will be helpful when I define my limit. So in this sense, these are off-shell diagrams because omega is now independent from k, so omega squared is not k dot k. And now each diagram that I had, which was a function of the a special momentum only, now it depends on n external variables in an endpoint function. So why this is useful? Because using these new variables now, I have the liberty to define this limit. So in this limit, not only I'm sending all the external energies to zero, so this is a slightly different than sending KT to zero, which was only the sum. Here I'm now sending individual energies to zero. But at the same time, this is a double scaling limit. So I'm also sending the intermediate masses to infinity, but in such a way that I keep the product fixed. So this is helpful because sending the external energies to zero, this is somewhat similar to sending the total energy to zero in the sense that the correlator will still pick contributions from early times when eta goes to minus infinity. So you still have this flat space picture, but unlike the massless amplitude limit that I defined before, now because I'm also sending the mass to infinity, the intermediate propagators in the intermediate propagators, it's true that the energy scales, the co-moving energy, the physical energy k over a scale factor goes to infinity, but at the same time, mass is also cranked up to infinity in such a way that these are comparable. So I expect that the intermediate propagators will be massive in a flat space regime. So concretely, in a reduction formula that I will show you in a second, so can you tell me, sorry, how much time do I have? Because now I cannot look at the clock. I forgot to bring my phone. Hello, Anish? Okay, maybe I can continue.
Hello, hear me?
Yes, I can hear you.
Yeah, sorry, there was something in my microphone. Yeah, so we still have 20 minutes.
Okay, 20 minutes. Very good. So I will tell you a reduction formula that in this limit expresses the correlator in terms of a massive Feynman graph in flat space. So the massive graph comes from amputating this diagram. So you just chop off the external legs. So there are a set of four momentum characterizes this diagram in flat space, but there are two differences. First of all, because I'm sending the external energies to zero, this four momentum will have zero energies, so they are purely spatial. And the spatial component also has a time dependent. So these are time dependent vertices. So at the end, the correlator will be an integral over this massive flat space Feynman graphs. And meanwhile, the internal lines will be just massive Feynman propagators. So it is important that, unlike the previous case, the mass is preserved. So this is a flat space computation that you just do with the usual means, just Peskin-Schroeder, and at the end you will get a Feynman graph that depends on time through the through the redshifting of the spatial momentum. And once you have done that, in this massive flat space limit, the correlator reduces to a very simple form. So no matter how many vertices you have, how complicated your diagram is, on the right-hand side, you only get one time integral. So on the right-hand side, you can actually think of it as just collapsing the original diagram, the original bunch of vertices into just one vertex. So you have one time integral to perform instead of like many in the original graph. And there is a time-dependent vertex that comes straight out of a flat space computation. So through the time dependence of the external momentum, you have this time-dependent vertex. And then everything is just smeared with the bulk to boundary propagators in the original graph, possibly with some derivatives that were already present. So this is the general structure. So it is still less direct compared to the massless flat space limit because there is still one time integral to perform, but it is massively simpler compared to the original generic graph. So this sounds a bit abstract. So let me break it down with two examples, one tree level and one loop example. So the tree level example is very simple. Imagine that the external legs, actually in this case, I'm just considering the external legs are light but not massless, so they are conformally coupled field. Um, and then the interaction between the massive field and phi is a cubic interaction, phi squared sigma. And then you just compute this tree-level exchange. Actually, the first time that this object was computed was in 2018 by a paper by Arkani Hamid and company using the bootstrap methods. So we have the actual correlator, and then we can check whether our massive flat space limit is correct or not. So in this case,
There is a question from the
yeah.
audience. And it's asking, I'm a bit confused as to why the flat space limit should correspond to omega I to 0.
Yes, well, yeah, it's a bit confusing because you might think that okay, so sending energy to infinity should correspond to flat space, but this is so in the cosmology it is due to the scale invariance that this has opposite effects. When you send kt or omega to zero, so you have phases in the time integral that go like e to the I omega eta. So when omega goes to zero, actually the dominant part of the integral comes from eta going to infinity in such a way that the omega times eta is finite. So this is the reason. It's just because of a scale invariance, the combination of momentum and time that appear together. So sending momentum to zero actually corresponds to sending time to infinity. So in that sense, sending the total energy, for example, to zero was the reason that we were picking up the UV part of the time integrals, which corresponds to flat space. So as I said, you should not think of K or omega as actual energies of the processes. So these are more like specifying the co-moving scale at which the processes are happening, not physical energy scales. I hope this answer is useful, but if not, you can maybe send me an email and we can discuss further. So in this case, the flat space diagram is very simple. Just chopping off the external legs, you have a single exchange diagram. And then the intermediate propagator is just a Feynman propagator. So the corresponding diagram is just this simple, it has this simple form. And then the external momentum, as I said, should be inserted as a zero energy component and k divided by a scale factor. And once you do that and you insert it inside our reduction formula, the statement is that in the massive flat space limit, in this double scaling limit, the correlator should reduce to this time integral. And this is very easy to crunch with Mathematica. It spits out this analytic function, which is a function of this parameter. So notice that here I'm sending mass to infinity, but I'm also sending omega total to zero in such a way that the product is fixed. So this is a nonlinear function of this product. And this is a very non-trivial function compared to the massless flat space limit, where it was just a power law scaling behavior. So there's more information here, which is not surprising because I'm reviving information about the mass. And you can actually check that the computation is correct by directly looking at, for instance, the equation that the correlator satisfied. There is a bootstrap differential equation that the original diagram satisfies. You can see that the same is also satisfied by this equation in the massive flat space limit. Another more non-trivial example, in fact, for this example, we don't have, for the off-shell correlator, we don't have an explicit computation in the literature. So it's a fairly simple diagram, but because just quantum field theory in curved space is hard, there aren't that many exact computations. So just a phi squared sigma squared theory and a bubble contributions to the 4-point function. So in this case, the flat space diagram is very easy to compute. Probably it's the easiest Fondue computation you ever do in Quantum Field Theory 1 course. The diagram is UV divergent, so of course we use dimreg to regularize the UV divergence near d equal 4. The 4-point function takes this familiar form where mu is a renormalization scale, and there is a divergent piece. Inserting this inside our reduction formula again by putting the external momentum by equating the external momentum equal to 0 comma k divided by a scale factor, you get this logarithmic behavior in the contact terms. So there's only again only one time integral to perform, but the vertex is more complicated because of the logarithmic structure here. Even with that, you can still do it analytically with a little bit of more work, where xn, yn, and zn are some coefficients that it's just a schematic form of the final result. But there is an infinite bit that also appears in the correlator. But this infinite bit, it's not surprising that it can be absorbed into a contact term. So the contact term in this theory would be just a phi to the 4 term that can absorb this infinity. As I said, because there is no explicit result for this particular diagram to compare to check if our massive flat space limit is correct or not, at least what we performed was to check that our result is consistent with the spectral decomposition of the one loop. Because in the CTER, such bubble diagrams can be decomposed into a linear combination of 3-level exchanges. So we check that the structure of the massive flat space limit of the correlator is consistent with this spectral decomposition. You can ask me about this later. I won't have time to go through the details. And I also won't have time to go through the exact proof. So I just gave you 2 examples, but you can actually prove that this reduction formula is very general. It applies to any endpoint function with any number of vertices and any number of loops. You can ask me later if you are curious about the steps, but essentially there are 3. So it's about simplifying the mode functions. Instead of Hankel function, you work with the WKB approximation in the massive flat space limit. And there are also 2 more technical points that helps you to simplify the in computation. So let me actually remind us of the elephant in the room, because from the very beginning, I was advocating for a relationship between correlators and amplitudes. And I wanted to really get a massive amplitude on the right-hand side. But unfortunately, what I have here is a massive Feynman graph, which is an off-shell graph. So explicitly, just p squared on the external legs wasn't 0. So it was just an off-shell for momentum. Therefore, what I have is really a relationship between an off-shell correlator and an off-shell graph. So this is still far away from a bootstrap point of view where you want to be on shell on both sides for this relationship um, to be most useful. But still, I mean, we could do some checks, and it's still a nice consistency check on the correlators if you are able to extend them to off-shell correlators. So there, you might ask if it is possible to find some unshelled version for this massive lattice space limit. So this is a work in progress. There are some nuances related to I epsilon prescription, but I'm happy to discuss if there were questions of how to go beyond this off-shell limit. But this off-shell limit, on the positive side, is actually useful for observation. So the reason is that so far I was saying that I'm looking at this extended set of kinematics, which had additional variables, the energies, omega. And then the massive lattice space limit required me to have access to omega going to zero limit of the correlators. So this might seem very unphysical because how am I supposed to actually have access to such correlators? And then how do I take the omega going to zero limit? In fact, in certain class of models, you are actually in a situation where omega is small compared to k. So first of all, there is an omega as sort of an independent object. If your light external fields have a non-trivial speed of sound, so if you break the Sitter boost, for instance, in the effective field theory of inflation, which for the purpose of this talk, you can think of them as P of X theories, where X is the kinetic term, and then you expand this theory around the time-dependent background and fluctuations around this background, which are characterized by this pi, which sometimes you can call them the phonons of inflation. So these are the scalar perturbations during inflation, acting like phonons in a superfluid. So the corresponding effective field theory for pi lets pi to propagate with a reduced speed of sound, which is CS. So in this case, if you actually look at the mode function in the Sitter, the propagator of this phonon, it behaves like e to the I CSK eta proportional to this factor, and this really accords with the non-relativistic dispersion relation omega equals CSK. So if CS is small, then you're really looking at an off-shell correlator with a small omega. So this is really what the massive lattice space limit is sensitive to. So of course, observationally, CS cannot, if CS literally corresponds to the scalar perturbations, it cannot be very small because by symmetries, if CS is small, you will have some additional operators that are cubic operators that will contribute to the three-point function, and the three-point function is bounded by Planck data. So CS cannot be very small, but it can still be much smaller than 1. So there is a window in which our massive lattice space limit applies. So the massive lattice space limit now translated into the language of the speed of sound and mass corresponds to having a speed of sound that is small and the masses that are of order Hubble divided by the speed of sound. So remember that we wanted omega times mass to be fixed. So this means that CS times m or CS times mass over Hubble is of order 1 in order for our formula to apply and the corrections to be under control. So in this window, this is a window of opportunities where diagrams like this, so for instance, you can look at the exchange diagrams contributing to the three-point
Hi,
function.
one more question
Yeah,
from Pratik from the in the audience, and taking some limit on omega explicitly while leaving the other components unchanged
yes,
breaks Lorentz invariance in
yes.
some sense. Is it true?
Yeah, that is true. Yes, exactly. So in that sense, I'm also breaking the Sitter conformal symmetries or breaking Lorentz invariance. And that is actually what is helpful here because, as I said, this is a model where your scalar perturbations have a speed of sound. So you break Lorentz symmetries in the UV or generally on the curved background, you are breaking the Sitter conformal symmetries. Absolutely. Yeah. That's why our limit is useful to be applied to this case, to the EFT of inflation. So you can, as I was saying, you can look at the contributions such as exchange to the three-point function of these phonons. So these are at the end related to the curvature perturbations zeta that we actually observe. So these are the adiabatic fluctuations that we observe on the sky and the CMB and larger scale structure. For instance, you can compute the one loop corrections to the three-point function.
We
So
have
on and so on.
5 minutes left.
Yes. Um, And then you can couple your massive field to this phonon. So the phonon has an approximate shift symmetry, so you can write down leading order operators like pi dot squared sigma, nabla pi squared sigma, or if sigma, for instance, is a charge a scalar field or a fermion, so the leading order corrections have to come from one loop corrections. So anyway, the message is that you do not really need to compute these diagrams in the sitter in this limit, because the massive flat space formula, the reduction formula, already gives you the leading order correlator in a small speed of sound regime. So this is very exciting because just there are no explicit formulas. So either you have to do it numerically or with some semi-analytic methods. But here we have a systematic control that at least at leading order in the speed of sound, for instance, you can compute the one loop corrections to the 3-point function. And that is what we did in this project. And previously we had done the three-level computation. Although for the three-level computation, you can also compute it exactly using the bootstrap methods. So for instance, one interesting signal that we recovered, so here we are looking at three-level, so you have the exchange of a massive field. The massive field is relativistic, so it has a speed of sound. It doesn't have a speed of sound. It propagates at the speed of light, and the external legs are slow. So these are some sort of supersonic particles that is being exchanged during inflation. And looking at the shape of the 3-point function, the shape of primordial non-Gaussianity, which is defined by this combination. So here I'm looking at a triangle. So K1 plus K2 plus K3, the vectors are 0 because of conservation of momentum. So you are in a triangle shape. You're looking at the triangle shape in primordial non-Gaussianity configuration. So you have two sides. One is the long mode, the smaller momentum, and the short mode, the sorry, the longest wavelengths, the K long, and the shortest wavelengths, Ks. And then you can look at the shape of you can look how the 3-point signal changes as you make this triangle squeezed. And we found that when you have this parameter Cs times m over h less than 1, there is an interesting regime where the 3-point function features a bump, a resonance in the squeeze regime of the 3-point function when the squeezing parameter is of order alpha. So this new shape of non-Gaussianity was actually used very recently as a new template for primordial non-Gaussianity to reanalyze the Planck data. So this was done by a group in Cambridge, and also to analyze the Boss galaxy data, looking for the signatures of such particles. Of course, there were no discovery of such particles, but it was still interesting that these ideas can sometimes give you new shapes for primordial non-Gaussianity that go beyond the usual templates, equilateral, orthogonal, and
We have
local.
1 minute left.
Yes. So we also did the analysis for one loop, although for the one loop, such bump do not arise. The shapes tends to be very close to equilateral. So let me summarize with some future directions. So first of all, as I say, that the reduction formula that we found was an off-shell flat space limit. So it would be very interesting to find an on-shell massive flat space limit where the natural candidate would be that you send KT to 0 and you send mass to infinity, and then you fix the product fixed. So as I said, so this particular limit, you might expect that on the right-hand side, you recover a massive amplitude, but there are some nuances regarding taking the I epsilon